It is my pleasure today to share some of my recent research. And today's topic is about the invertibility in image processing and restoration. So we all know in computer vision, there are different types of tasks. One of the popular tasks is image classification. And usually we use some discriminative model to do the prediction. So given an image, we will have a model that generates some label that represents the image. On the other hand, there is like an opposite task where we can have some generative models given some label where we can generate the corresponding images. So this like some reverse task, but in practice, it is impossible to generate the exact cat we see here because given the information like a cat, we only have a very little information. But if you look at the task of image processing, so the input may be an image, and then the output is also an image. So we may think, can we have learn a model that could perform two tasks at the same time? For example, given an image like on the left, and we do some image processing, we generate the right image. But at the same time, we can undo such a process and restore the original image. So, so in such a task, we may want to have some as invertible as possible model, so that we can have a model that to do the forward and backward inference. And we can generalize such a notation to different modalities. For example, image, video, image set, raw data, or some binary encoding. Let's take an example. If the left side is image and on the right hand side is binary encoding. And what we want is we want to minimize the amount of information in the binary encoding. And such a task would be like image compression. So we want to explore such a framework and see how this type of model can have other functionalities in other tasks. So in this talk, I would summarize some of my work, recent work in different types of tasks. For example, I will talk about the invertible image signal processing, where we have an invertible model that performs a transformation between the image and the raw data. In the past, we only have a image signal processing that performs the raw data to image transformation. And there are also some recent paper that try to recover the raw data from the RGB image, and we unify the two parts in the same framework. And we will also study image compression, essentially doing the the conversion between the binary encoding and the image. And we saw that we can achieve state-of-the-art performance, using some invertible models. And we will also look into other tasks where we see between image and video, between image and novel view synthesis model, between image and audio, and even between image to image translation. And we see how this kind of model can achieve different types of functionality and even improve some very challenging tasks like image compression. So I will cover 5 applications in this talk, and all of this model will follow the similar principle where we want to design an as invertible as possible model. So there are some benefits. I will talk more in the rest of the talk, But in general, we can summarize. First of all, this kind of model has reversibility, and it also has compatibility. I will talk more in the later part. And saving storage, for example, we don't have to say, for example, let's say raw data and RGB image. We only need to keep the RGB image, and at the same time, we can recover the raw data. That's very large, usually tens of megabytes. And there is a related task that's steganography or watermark. It can be also used for hiding some information. And we also saw that it can improve the compression capability. So there's some related work in vision conferences and SIGGRAPH. For example, in one of our recent work where we can hide the video in audio. That means given a video and some audio we want to hide, and then we can generate the encoded audio, and then we just send the audio to someone else. But the receiver can recover the original video. There are other papers, for example, invertible grayscale. So there was a work about converting a colorful image to a grayscale image, but we can also recover the original grayscale image. And there is a follow work by Jia also about deep half toning. In super resolution, there is a work, invertible image scaling, where the authors use some invertible model that downsample the image, but at the same time can recover the high resolution image with high fidelity. And one more example is where we can convert a stereo video to a monocular video. But at the same time, we can recover the stereo video from the monocular one. So some of our research, inspired by this related work. So in the first project, we will talk about the invertible image signal processing that corresponds to the connection between the raw data and image. So, so we have found that the raw data is very useful. So first of all, professional photographers can edit the image better using the raw image data. And in one of my work, we saw that that's learning to see in the dark, where we saw that using deep learning plus the raw data, we can reconstruct high quality images in an extremely dark environment where the illuminance is less than 1 lux. So the raw data is very useful, but unfortunately, usually the raw data is very large. It's tens of megabytes, and the raw data may be discarded when during the data storing, transferring or sharing, because they're too big. We don't want to keep it. We just keep RGB image. And our objective is can we construct an as invertible as possible model, and we can get access to the raw data without explicit storing. And actually, we get this raw data from the RGB image. So we can first have a look at the result first. So in a camera, it produced in the end it should be a high quality RGB image. But before the getting this RGB image, we will have the raw data. That's what the ISP would do, that transform the raw data to the RGB image. So some of the work try to reconstruct the raw data from the RGB image. And here we visualize the error map. And here are our results. So we first analyze why there is some information loss in the image signal processing, and why it's very difficult reconstruct the raw data. So this is a standard image signal processing pipeline in the ISP. So we can see that, okay, there is a denoising step. Okay, it will smooth out the information. There, tone mapping, JPEG compression that will lead to data, some information loss. And what we think is, if in the RGB image, if we can somehow hide some information about the raw data, maybe we have a good chance to reconstruct the original raw data with very high fidelity. So here comes our framework, and in principle, it's quite a straightforward model where we have invertible model F. Okay, that's basically invertible neural network, and that converts its raw data to the corresponding RGB image. And using the same network during the inversion, we can recover the raw data with relatively high PSNR, like 45. And with the raw data, we can have other image editing tasks, for example, HDR reconstruction, image retouching. Yeah. So it will be very valuable. So our pipeline is based on having, building a neural network with multiple invertible blocks. Okay, and within each block there are a fine coupling layer and invertible one by one convolutional layer. So these are commonly used in invertible neural network. And then the forward pass try to mimic the process of the ISP. But there is one step where we want to simulate the JPEG compression. So that, because what we want in the end, we don't want to save it as a PNG file, which is still kind of big, and we want to save it as a JPEG file. So the affine transform, affine coupling layer would have such a formulation. I would simply skip this part. And we'll also look into how we can simulate the JPEG compression step. And within this JPEG compression, there is some quantization step when we use some Fourier transformation to approximate this quantization step, so that the JPEG the simulator becomes differentiable. So and we also try other types of architecture. Other types of architecture are basically encoder decoder like architecture, and they don't produce the same quality as our invertible neural network would do. So in the end, we evaluate our method on two types of camera, the Nikon camera and the Canon camera. And if we look at the results, we achieve quite high in both RGB image and the raw data reconstruction. So for the RGB image, in the end, we get PSNR around 37, and for the Canon camera, it's 33. For the raw data, the PSNR is 45 or 48. Yeah. So there is always a trade-off between the quality of RGB image and the raw data reconstruction. I think the trade-off would depend on the actual application. And at the same time, we indirectly achieve the raw data compression, because we can get the raw data from the JPEG image directly. So we can achieve a compression rate around 35 or 27 X. So it's better than the Lossy PNG file. And there is no much difference using the ground truth raw data or our reconstructed raw data for retouching or HDR reconstruction. So we can see that using some invertible neural network can, as more functionality to a very common ISP pipeline. And due to this work, we are also inspired to have more exploration. So currently we are working on the extension of the work, and we can see whether we can reconstruct the raw data for video. Saving the raw data for video is, very memory demanding. There are so many frames. The raw data is so huge. So we working on this when we currently also achieve reasonably good result. And next, we also look into another type of task. So image compression. So it's a task that has been studied for a long time. So there are deep learning approach. There are classical approaches. So we would compare our model to them. So let's look at how the image compression method will work. So given an image, let's say X, you will go through a function, maybe GA, and you produce some feature, this Y. Okay, there is some quantization and encoding. So we call it arithmetic encoding, because we get some binary encoding. And during the decompression, we will reconstruct the feature, and then we have a decoder to generate the reconstructed image. So for traditional image compression, we may consider to use some Fourier transform, so like in JPEG. So nowadays we have some learning-based approach. So this DCT will be replaced by some encoder or decoder. So so for this part, the arithmetic coding, we basically just use some state-of-the-art coding method. What we want to focus on is maybe the encoder decoder can be replaced by a better architecture, and we think of the invertible neural network. So so there are very nice property about this kind of invertible neural network, because we have bijection between the input and output, and and we can compute this forward and backward, also quite easily. So it can be also used for generative model. There are also some attempts in using invertible neural network for image compression, but they were not quite successful yet. And we find that if we only use the invertible neural network, because as we see the building block somehow limited, a fine coupling layer or one by one convolution. There are not many different types of blocks we can use in the invertible neural network, and we try to address this issue. So here is what we design. So first of all, we don't directly put image into the invertible neural network first. We have some dense block and convolutional block. It serves as like also similar to some encoding, but it's like a residual block here to do some feature enhancement. And then after that, we would do add some invertible layers, pixel shuffling layer that is essentially to do the reshaping of the tensor, one by one convolution coupling layer. So it's a popular layer. And then there is a stage where we want to reduce the dimension of the feature. So suppose now we have a feature map with 64 channels, and we want to do the reduction. What we can do is, okay, we average all the 64 channels and get a single channel. And in such a step, we can reduce the amount of information in this channel squeeze step. We also add one more attention layer to enhance the feature. And so that's what we do, we some feature enhancement in the beginning, and then do the average, and then have this hyper prior that's from other work, and then during the back work when we try to reconstruct the image, since here we only have a single channel, we just copy the single channel 64 times and then put it back. So there is another decoder to reconstruct the original image. So having such a design, and we compare our method to state-of-the-art learning-based method. This you see in AI-related conferences, there are a lot of paper, but the state-of-the-art is a conventional method, VTM 12.1. The pink curve here, we are close to it. I think among the learning-based method, we are best, and we may be slightly better than the VTM on the click data set, but not much. I think comparable to the VTM. But we believe the learning-based approach will become stronger in the future. And there is some visualization of the result. This is our result. This is ground truth. Here is the VTM. Here is JPEG. JPEG doesn't give us any good results here. Okay, so after we look into the image compression, and we interested, okay, another kind of cross-model conversion. Okay, maybe can we do video to image conversion? Can we reconstruct the video from a single image? So we would do more, not just a video. So nowadays we have many different types of multimedia data. For example, we can have stereo image, stereo video. For live photo, it's actually a short video. And there are Huawei phone that produce dual view images, because in our smartphone today, we have different cameras. We can merge them together to produce this dual view image. And unfortunately, it's not easy to share this kind of data because, for example, I don't know how to share live photo easily with my friends, except for AirDrop. And this kind of data will become also larger and larger. And maybe we think an embedding image can be a good interface for storing this kind of multimedia data. This we call it a reversible image conversion task, and it has some advantage in it's a backward compatible. For example, in a autonomous driving car, maybe we come up with a new way, some image set. Okay, we want to store it, but it's not easy to share in the standard hardware system. That's a backward compatible, and also at the same time, because it's just an image, it can save the storage cost and easy to share. So there's some existing work which is called video snapshot here. It can performs the conversion between short video and embedding image. And there are other paper I have introduced that stereo image and embedding image conversion. And they decide different types of model. And what we want maybe, and also these models are task specific. Can we have a unified model to this task, and we can even do more? I will show it later. So we inspired by the previous work in the image compression. We designed a general framework for this kind of task. What we have is given an image sequence or a video. Okay, we first have a relation module to learn essentially still to enhance the features in this image set or a video, and then put them through invertible embedding module and using the similar trick. And we can even have a lower resolution image here as the embedding image, and we can reconstruct the original image sequence. So this is an extension of the prior work. So we try such a framework on at least 7 tasks. Some tasks has been demonstrated in other papers. There's some new tasks we will show. Compared to the video snapshot, where in the embedding image there are clear artifacts, some high frequency artifacts, and in our result there are no such artifacts. Here are the reconstructed video frames. We zoom in and we achieve very high PSNR in the reconstructed video frames. And here the some other demonstration. So we can reconstruct such a high resolution, high frame rate video from this low resolution, low frame rate video using our framework. We can also generate a GIF file from an embedding image. So actually this is quite similar to the video task. We can also do the mononizing binocular images as the prior work has done, and we also do better than their task-specific task. So that means using the monocular video, we can generate the left view and the right view at the same time. So for dual view images, we can also use our framework to reconstruct the zoom in image. And this is a task I find also quite useful. For example, in Photoshop, sometimes we may have multiple image layers, and we do the image composition. After the composition, we basically lose the background information, some part of the background information. So when we want to get access to the background information, maybe we need to get back to the original Photoshop file, but that's not easy to solve. Usually big. If we have such a model and we can somehow do the decomposition, okay, we can reconstruct the high quality background from this embedding image, because we somehow inject some pattern information in this embedding image so that we can also reconstruct this part. So in an even more general scenario, we can embed the image set even in a single image. This is embedding image, and these are the reconstructed image. They look visually similar to the original one. So as we can see that such a model is very powerful to compile a lot of information in a single embedded image. So we also compare with other models. So actually, we originally start with autoencoder or simply invertible neural network, but they don't achieve very high quality result yet. So they are also one of the potential models. So later, we also looked into the very hot topic, no-wave synthesis. So we see there are a lot of results, no-wave synthesis result, especially with nerve. So we think how we can make, how we can store such a model, and how we can store a no-view model, share it more easily. And a single JPEG image achieve such a task. So given a no-view synthesis model, so there's some issue today. It's not easy to share on the social media or view on the phone unless we have the corresponding app or plugin to decode it. Otherwise, you may look strange, and also it may be large to share. So maybe a single JPEG image can be a file for sharing. So we consider a noise synthesis model, MPI, and we want to embed 32 images in a single image, the embedding image, and at the same time we can reconstruct the MPI model. This sounds very challenging because we embed totally 128 channels in 3 channel JPEG image. We believe such a task would have some benefit. First of all, we have an embedding model to have this embedding JPEG image. Some user, if he cannot see, for most user, maybe just see a 2D image. But if we have the plugin, then we can decode the MPI model and generate 3D scene. So here is our model. We have some task-specific design for this MPI model. So first of all, we have this feature fusion stage, and we combine the information from the input layer and the input alpha layer. And then with such a design, we have a unit-like model, and we purposely add a lot of data augmentation, JPEG compression, color transform, random crop, so that even we crop the embedding image or change the color of the embedding image, we can also reconstruct the original MPI model so that we can do the novel view synthesis from a single JPEG image. Okay, maybe we can jump to see some results. So this is embedded image where we save the novel synthesis model, and here are some results where we would do some novel view synthesis. So this MPI model, not the very state-of-the-art a few years ago. So it can offer generate the result with relatively small baseline. But compared to other alternative solution, we can see that the our model can generate the result that's very similar to the ground truth MPI model would provide. Okay, and lastly, there is a recent work where we want to add one more functionality to the image-to-image cancellation. Or maybe that you have seen some work. Okay, maybe we can do the day-to-night transformation and then night-to-day, but it's not highly invertible, meaning that we don't always reconstruct the original result. If we apply day to night and then night to day, maybe we get a different result. So can we have some restorable image operator that we can always get back the original image we start with from. So there is, I had published a work in the past about fast image processing. So so we have a lot of image processing algorithms, but we saw that okay, we can use a convolutional neural network to approximate such a process. For example, suppose we have state-of-the-art dehazing algorithm. Maybe it's filtering based or optimization based, but we can use a convolutional neural network to approximate such a process. But can we add one more functionality to it? Can we, from this dehazed image, can we reconstruct the original AC image? So we want to study such a task. So for example, in the first row, we can use our model to generate the desirable image processing result. At the same time, we can restore original image because we don't want to keep the two copies. That, you know, for example, in our smartphone, if we have this image and we do some image processing, we get this one. Maybe we don't want to get two. In our smartphone, we don't have a lot of storage. So if we had add such a functionality, we can also can infer the original image from the this results. So that may be also quite useful. So also give us the very original, image. What for example, what this person look like. Okay, in the smooth the image, we don't see the detail. So what we design is originally we only tried the purely invertible neural network, but we find that there is some limitation of the invertible neural network. So it's hard to approximate a lot of image processing operators. So we design a two-branch neural network. The first branch, okay, would be purely invertible, and there is a second branch that's non-invertible, and then there are two parts. One is from this head from this invertible part, and there is this delta from this non-invertible part. At the same time, we want this part to be minimized, to be close to zero, because during the inversion, we would only have this single image part, and we will fit into zero for this part during the inversion. So during training, we want to minimize this. And we also have different types of differentiable compression module that's not pegged to the JPEG. The trick is very simple. During the backpropagation, the gradient on the compressed image here and the uncompressed image, we assume that are the same, and that works well in practice. So having such a design during the forward pass for example, to do the image processing, we will go in the blue arrow in this path. And then in the backward pass, we will only utilize the red path. We essentially ignore this path because it's not invertible. We cannot go back. So this is what we propose. We have a quasi-invertible neural network. So some applications, for example, suppose we have a original image like this, and we have processed the image, but we can also restore the original image, and we can add more image editing, for example, sharpening, style transfer on the original image. And secondly, for some image, maybe after the processing, it may be overexposed, but our approach allows us to reconstruct the original image, and we can do the image editing on the original image. Because if we do some image editing on the original, this process image is basically purely white. That's not desirable. So we evaluate our method on 10 tasks. So we achieve very good results in terms of PSN and SSIM, except for the style transfer, because it's somehow stochastic like process. So, but the visual result is actually quite good. So we can also work on different JPEG quality. So that's some of our results. And here are some visual results about approach. Even from this highly transferred image, we can reconstruct the original image from the, it's hard to tell what the original image from the image with style transfer. Our approach can reconstruct it from such a JPEG image. Okay, so so far we have seen this kind of as invertible as possible model can enable several different tasks, and we believe it may be also extended to other modality. For example, for point cloud or for the multi-view images and so on. So that would be interesting how we can add the invertibility to some of the model we have, and where we can save the data, we can add the compatibility. So that's all for the presentation I would like to share today. So I think we would still have some time, maybe we can take some questions. So any questions?
That was a very interesting talk. I had a question, just general understanding. So you described a lot of different tasks, and I'm just trying to understand how specific the models that you're training are for each of those tasks. Like, is it per image, per data set, or you could train one model for a kind of task and you think it will generalize for every image that you see in the future?
Yes, so very good question. So our model is not pegged to some image or some scene or some data set. We only need to train a single model, and that works for any data. So it's not like, for example, nerve, where maybe we need to train different nerve model for each scene. Okay, we only need a single model, and that can perform, for example, image compression. So we would train on a big data set for this kind of model.
And a second question is about sort of parameterization. So if you were kind of, I think, approximating some more complex image processing operations, just say, for example, blur, and you can adjust some parameter of the blur, the size of the blur, the strength of the blur. Is there that same parameterization ability in these invertible or quasi-invertible networks that you described, or do you train a different network for a different level of blur, or I mean, whatever the operation, a different level of style transfer? Or...
I see. Very good question. So so for different types of image operators, we train a different model for their processing. So for L0 smoothing, we would train a model for style transfer. For particular, with this screen style, we would train another model. And there is some way to add the some hyperparameters, like the degree of smoothness injected into the model, but we didn't explore this part in this work yet. But in my previous work in 2017, we have shown that this can be achieved.
My final question is, it seems like magic. So do you have some idea of like why it works, or how much information you can pack into one image? Because you might imagine, or I would think, like if I took a large number of entirely random noise, maybe it might not work to shove that all into one image, for example? Is it just because there's a lot of regularity or something in images, or any idea about that?
I think well, what we see, I think the model tried to inject some high frequency pattern that into the image, but we cannot see it from the image visually. And then the model, when it tried to decode some hidden information, it tried to utilize some hidden high frequency image, because usually a natural image we would assume is somehow smooth locally. So that's what I feel. And if we look at some of the other work, if you look at some the video snapshot, we see the embedding image. So they in this task we are doing the video to image conversion. So it tried to hide the information of video. I assume in this kind of high frequency pattern. I'm not sure whether you can see clearly on the Zoom, but I can see that there is some high frequency pattern. So that's my intuition. Yeah. So it would be interesting to see how the model actually tried to embed some useful information in an image while it looks the same, like the same image, to us. Yeah. Yeah, thank you.
I have a question. Hi, thanks for the talk. So my understanding is that the end user, like when the end receiver, would need to be sent like the task-specific trained model in order to decompress, right?
Yes.
So in terms of memory, how does that compare to like a more traditional codec? So if I'm sending both the raw or the JPEG, the compressed JPEG, and also the model, how does that compare to, say, like just sending the raw itself?
Good question. So, well, we would assume the decoder, the decoder can be used multiple times because it's the same model for different images. So the model, I think it's much larger than the image, I would say, but it's just like an app, maybe in our smartphone or a software, some software in our computer. We only store it once, but we can decode for any image. For example, if we want to share a live photo, maybe we can send it as an image, and we use the software we already installed in our computer to do it. So and then in that case, I think it would be easier, and sometimes it's not easy to share a video, especially a high quality video, but we can share an image also more easily in a lot of platforms.
Sure. Okay. Do you have some kind of like a rough approximation of like how large this model actually is with all the parameters involved?
Okay. I don't have the exact number. I think in the scale of millions of parameters. And the running time, as far as I know, for 1080p image, it's roughly 1 second in terms of the running time. But on GPU, so it's slower than the traditional codec. Yeah.
Okay,
Maybe you can embed the model in the image too.
The model is probably too large, I would say, to embed in an image. So it would be cool to, yeah, so we actually study some small lightweight decoder, and that's a very small with very few parameters, so that we can make the decoding part to be very fast. We don't want the decoding to be heavy. Yeah, so that would be a good direction also to look into to make it even more practical. Thanks. Thanks for the very good question.
Is there any questions from audience? Okay, I have one. I think it's one really quick question. I think it's kind of similar to the ones that people asked before. So I think one of the tasks that you showed, you try to reconstruct left view and right view from a monocular view, right? And I was wondering, so for this, you also train, for instance, the left view, right view, and does this model like can it generalize to, like, for instance, different baselines, or it's just like for a single fixed thing? And and once you train, is there any controllable parameter that you can just try to increase the baseline, kind of like these controllable synthesis? Do you have these?
So we don't have any assumption on the baselines. We just assume that, okay, there is a left image and the right image, and we want to embed it as a single. Here, I think the embedding image, maybe the left image. Okay. So we don't have any notion. We don't even know in the model. In the model, it doesn't even know this is stereo image because our framework is designed to be very general. We can embed any types of image into a single one. So it's not restricted.
I see. So even if, for instance, if you do this task, for instance, if you train with, like, for instance, small baseline, and say at test time you apply a large baseline, and it will still kind of work.
We didn't test the exact setting you mentioned, but I think it should work. Yeah.
Okay.
So we don't have any assumption. So you know, in the input, there is no assumption that this image patches must be related. It can be, unrelated at all. In the final application, we can also reconstruct the 5 unrelated image.
Okay. Okay, so if there's no further questions, let's thank Qifeng again. Thank you so much for your talk.
Have a good day.